Okay, so instead of giving a broad sweeping overview of what I've done in the past 2.5 years, I want to focus on really the studies that I've done, that I've worked on, that are kind of at the core of the theme of the initial research project. So I won't talk about anything on decision times, experiments, mixture sets that I've been working on, and instead just focus on mostly the topic decision-making under risk and how that relates to information. Now, there is a workhorse in economics that we use almost every day and in almost every context, and that is expected utility. So this study that I just put up, and I could have put up any arbitrary study, is a study, Holt and Laurie, is the standard method by which people elicit risk preferences from subjects, and this has about 8,000 citations. So really, expected utility is one of the core pillars of modern economics, and there's sometimes critique from the outside on leveraged on economics that it's somehow, that's kind of like not sensible, like people don't really maximize expected utility. But I want to focus on two critiques that are perhaps a little bit more nuanced. One thing is that if you do model selection on a variety of different models, let's say you throw in expected value maximization, or you throw in prospect theory or other theories, then often model selection actually either chooses simpler models or it chooses more complicated models, but somehow expected utility is somewhere in between and often dominated by either direction. And there's, of course, a question why. But also in the, let's say, more philosophically inclined economics literature, it is also the question whether expected utility maximization is actually normatively convincing, and there have been arguments brought forth that perhaps this is not the case. So let me first, so one of the studies is about a positive decision theory, the other one about normative decision theory. And so in terms of positive decision theory, there are various inconsistencies that people have with respect to expected utility, where we kind of know, okay, people don't really maximize expected utility, and expected utility is more of an approximation of their behavior. One of those in particular is that people tend to overweight small probabilities and underweight large probabilities relative to how much importance they should put on these when making decisions according to expected utility. From the perspective of normative decision theory, I want to focus on one critique that is perhaps it is not normatively convincing to impose on individuals that they should hold a single probabilistic belief, but perhaps they should be allowed to have a little bit more flexibility in their decision making. And perhaps hold more flexibility in their beliefs. And I'm going to talk in both about the positive part that I just described and then normative part. So in the positive decision theory study, this is a joint work with Patrick Dejohnette, also from Macedo, Luciano De Castro, and Antonio Galvao. We look at the following issues. So when you do this kind of model selection, then there are two strong competitors to expected utility. One is rank-dependent expected utility, which captures this idea of probability distortion that I just talked about. And it turns out that you cannot just rewrite expected utility and distort the probabilities a little bit arbitrarily, but you need to, because then you will your model will violate what is called first-order stochastic dominance. And first-order stochastic dominance is something that people relatively well obey. So your model will actually not be descriptively correct. So instead, Quiggin came up with this formulation of rank-dependent utility, where you instead distort cumulative probabilities. And there's a recent controversy about whether this is now a good model or not. But indeed, model selection would sometimes favor rank-dependent expected utility over expected utility. even though it has more parameters in some sense. And then there's quantile utility, which two of our co-authors have published papers on, and that goes in the other direction. It has less parameters, and it still sometimes outperforms expected utility when you do model selection. What you do in quantile utility is you just fix one quantile, let's say the median, right? And then you just, whenever you're being offered different lotteries, you check what is the median of this lottery, what is the median of that lottery, and you choose according to the median. So it's a very simple model, which essentially just has one parameter. It just has the quantile that you use. Do you use, so to speak, the value at risk, which would be kind of the 5th percentile? Do you use the 95th percentile, or do you use the median? And still, it's a model that describes behavior quite well. Now, why do these models actually somehow perform so well? Is one question. And then coming back to kind of the Holt and Lowry 8,000 citations used everywhere in economics study, how can we perhaps get a little bit closer to this kind of level of elicitation? So can we elicit something as complicated as rank-dependent utility as conveniently as expected utility? So let me just display to you how simple it is to elicit the expected utility model. Here you see something from the paper from Holt and Lowry, a table of decisions. So you ask the subjects, please choose between option A and option B in each of these rows. And most people will initially choose at the top rows, they will choose A, and at the bottom rows, they will choose B. If you do this, you can actually calibrate with reasonable precision an expected utility model called CRRA, where you can figure out, so to speak, for the individual, what is this row parameter that we have up there. And you do perhaps a bunch of these lists to make sure that you're not just catching up on some error. Right? So what is our approach? So we first formulate a utility function, and I'm going to just introduce you to this utility function, and then I'm going to relate this to rank-dependent utility. So in this utility function, we say we are not going to kind of maximize expected utility, but we're going to weight every quantile. Right? So the decision maker can attach a weight to a quantile. This is this WQ term. And then the decision maker evaluates the quantile, the quantile of the lottery at some utility. Now, if you, let's say, just have a W of Q of 1 for one particular quantile, then that is just the quantile utility that I introduced before. If you have a uniform distribution, then that is expected utility, but you might have actually something else. And what it turns out is that weighted quantile utility is just the same thing as rank-dependent utility. That is one insight from this paper that we had in the process. And this gives, so while this is in some sense just a rewriting of the utility function, it gives actually a foundation for rank-dependent utility that is different from the foundations provided before. So not in terms of we're distorting probability somehow, but we're just forming some sort of weighted average based on reasoning of the form, let me look at the quantile of this lottery versus let me look at the quantile of that lottery and compare them. And let me do a bunch of these comparisons. So in this lottery, I'm going to get 100, at least 100 with probability 1/2, but in this other lottery, I might only get 50. And then I do a bunch of these kind of comparisons and I weight them, and then based on these, based on the weighted average, I make my decision. What this does is, first of all, it gives some intuition why rank-dependent utility might be quite good, but it also gives us a new way of eliciting risk preferences. And that's what I want to talk about now. So let's say that we go and we use the same kind of utility function as the CRA model for the utilities. And for the weighting function, we are going to use a beta function. Then we can actually elicit these the parameters. There are 3 parameters of this utility function in a very simple way. And I would argue that it's almost as simple as Holt and Lowry. So what you see here is you see graphs where on the x-axis we have the quantile. So 50%, the 50% quantile is the median. The 99 is, well, almost the best outcome. And the 1% quantile would capture kind of, oh, what is really the risk for how much is at stake here. And so the red line, for example, in this linear payoff case, is just a fixed payoff. You're definitely going to get 100. The blue line is something that involves some risk. So with 50% probability, you're going to get something better or worse than 100. With 99% probability, you're going to get something worse than, what is that, 198, and so on, right? So the blue line involves some risk, the red line involves no risk. And so in our elicitation method, what we do is we ask the individual to shift the red line until the individual is indifferent between the blue line and the red line. And we do this just for a linear payoff that goes from 0 to 200. Then we shift this whole thing up by, let's say, 100 units. And then we also consider it with curvature. And then each time the decision is roughly the same. And it turns out that this can uniquely pin down our utility function, UWQU, with these parameters rho, alpha, and beta. Now, this is admittedly not quite as simple as Holt and Lowry. We need to ask a few more questions because we need to find 3 indifference points instead of 1, but we're also estimating 3 parameters instead of 1. But on the upside, I feel that it is much more intuitive due to the visual representation of the risk. So I can really see how much risk I'm encountering as opposed to having to process this by doing some sort of number calculation. And we are planning to do an experimental study, of course, on this. But the key point of this is that it provides a direct test of constant relative risk aversion against beta probability weighting. So you can see in the end how far are the beta weights, this alpha and beta. How far are they from 0, and then how far is the CRA, the rho away from 0? And so in that sense, we can speak to some of these recent debates over whether people do indeed engage in this kind of probability weighting or whether people just have standard risk aversion. Now, let me move on to the second study. I don't know whether... Yeah, I still have enough time for that, but I might have to speed up. So this is now a normative study called Preference for Verifiability, where I'm looking at some of the ambiguity models and I'm providing a very different foundation for why we would want to behave according to these kind of models of ambiguity aversion. Now, let me briefly introduce what is ambiguity aversion and what are these models. So the Ellsberg paradox is a famous paradox where I would say even many kind of hardcore expected utility maximizers feel a little bit difficult to justify choosing expected utility. And this includes Savage, who is one of the founders of really the rational foundations of expected utility maximization. So consider the following problem. You have an urn, and the urn has, with certainty, 30 red balls. And then it has some yellow balls that are yellow and black balls. And you don't know the proportion of the yellow and black balls, but you know that there are 60 of those in total. Now, you're being offered to either bet on the red balls or you're being offered to bet on the black balls. And it turns out that most people will choose to bet on the red balls rather than betting on the black balls. So they will choose gamble A over gamble B. Now, however, this, according to expected utility, or subjective expected utility, indicates that you actually believe that there are slightly more yellow balls than there are black balls in this urn. Now, when you are then being offered gamble C versus gamble D, where you can choose to bet on either red or yellow, or you can choose to bet on either yellow or black, most people actually switch. So they will prefer D over C. And again, D offers you, so to speak, a fixed probability of 60%, of 2/3. While you actually don't know what the exact probability is in gamble C. So people prefer A over B and D over C. And some authors have argued that perhaps this is actually rational, because you should be allowed to entertain perhaps that you have a whole bunch of probability distributions. Now, one of those examples that is mostly intended as a descriptive model, but again, Gilboa and co-authors have argued that perhaps this should also be a normative model, is maximum expected utility, where you entertain a whole bunch of probability distribution and you minimize your expected utility over these different distributions. Another alternative is Choquet expected utility, where you just have one probability measure, but this probability measure is not necessarily additive. Some key point of these models is that your ambiguity attitude is completely separable from the utility level that you achieve, and this is captured by an axiom that is called certainty independence. Okay, so here's one set of research questions in this overall study. Is there perhaps some sort of normative compelling reason for maximizing something like maximum expected utility, Choquet expected utility, that is other than just expected utility is too difficult? In other words, can we justify, for example, normatively that we should obey certainty independence, which I'm going to come back to in a moment? And my answer is yes. There are certain situations in which it turns out that certainty independence is normatively compelling. Here I've sketched these. Consider, for example, CO2 emissions of a company. A company that emits CO2 might want to, in a decision in which they choose different ways to mitigate, they might want to prove to their stakeholders that they have done well. If you are donating money to an organization, you might actually want to donate to an organization where ex post you can verify that this money that you've donated has done something well. When you eat fast food that is potentially unhealthy, you might focus on the ex post verifiable information and make sure that nothing verifiably bad has occurred. Let me make this more precise. So quite often we make decisions in which the outcomes, decisions under risk and uncertainty, in which the outcomes are not perfectly observable. So when a firm tries to mitigate CO2 emissions, the measures that they take, the amount of CO2 that they've mitigated is perhaps not ex post observable, because it just goes into a bunch of other CO2 in the atmosphere. health consequence of fast food, you don't observe immediately perhaps the carcinogenics that you're eating. And so decision makers may care about either verifying or obfuscating whether good or bad outcomes have been achieved. Now, given that I'm restricted in terms of time, I want to just briefly talk about what this paper now does with this idea. It introduces two models called expected verification utility and expected obfuscation utility, which are both special cases of maximum expected utility and Choquet expected utility. I provide an axiomatic characterization of when it is normatively convincing to maximize these. And I apply these to, for example, the CO2 reduction of firms in order to obtain a model of greenwashing versus legitimacy seeking. It's somewhat surprising. I started out initially just with this idea of greenwashing versus legitimacy seeking, and I was surprised to find out that actually the models match the ambiguity literature so well. So with that, I would like to conclude and thank WIAS and Waseda University for my research time here.